Hello students, in this video we'll discuss recursion relationships for the Laguerre polynomials. Let's recall the Laguerre polynomial Ln of x is given by the Rodriguez formula as e to the x over n factorial, and then n derivatives of x to the n e to the negative x, like that, okay? And so what I'm going to do now is I'm going to consider n plus 1 times Ln plus 1 of x, right? So if we thought about this in terms of Ln plus 1, this relationship would tell me that Ln plus 1 of x is e to the x over n plus 1 factorial, and then n plus 1 derivatives of x to the n plus 1 e to the negative x, right? So if I do this, what will happen to the n plus 1 factorial is it will turn into an n factorial. So this is going to be e to the x over n factorial, like that. And then I'm going to do a dn, n derivatives. I'll do one derivatives expression over here. So I do one derivative, I'm going to have an n plus 1, x to the n, e to the negative x, then minus e to the negative x, x to the n plus 1, like so, okay? And so from this first term over here, if I pull out the n plus 1, I just see I have the nth Legendre polynomial, right? So this is going to be just n plus 1 times Ln, the nth Legendre polynomial, and then minus e to the x over n factorial, n derivatives of what? Of e to the x, x to the n plus 1, like that, okay? And now here's an important thing to observe. What we're going to do now is I'm going to actually use the following relationship. So recall, if I do, here's a lemma, an important lemma doing these recursions. If I did n derivatives, if I do a derivative, n derivatives of x, f, right? Then what I can do is I can either do all the derivatives of f, right? So that will be x times dn of f, or I can do n minus 1 derivative of f, and then 1 derivative of x. So that'd be plus n dn minus 1 of f, right? And so that's just the Leibniz rule for dn in the operator multiplication by x. And so I have x times something over here, so I'm going to apply this formula over here. So using this lemma, which follows from Leibniz rule, this line becomes n plus 1 Ln minus e to the x over n factorial. And then I have dn, and then I have x times what? This is really x times e to the negative x, x to the n. That's my function f over here, right? So then this is going to be what? Then I'm going to use this rule. I'm going to pull out that x. So it's going to be an x, and then times what? Times dn of e to the negative x, x to the n, and then plus n over here, plus n, dn minus 1 of what? Of e to the x, x to the n, like so, okay? And now this term over here gives me an x times the n minus first Legendre polynomial. So this is equal to what? This is equal to n plus 1 minus x, and then Ln, and then minus this term over here. So minus e to the x over n minus 1 factorial, and then what? And then this dn minus 1 of e to the negative x, e to the negative x times x to the n. Great. And so now here what I'm going to do is I'm going to symmetrize this, and what I'm going to do to symmetrize this is I'm going to add and subtract in n Ln of x, okay? So I'll group that n over here, and so what this will give me is this is going to give me a 2n plus 1 minus x Ln minus e to the x over n minus 1 factorial times this expression over here, d n minus 1 e to the negative x, x to the n, like so. And then I have that extra negative n Ln of x, okay? So let's keep writing this out over here. This is going to be what? This is going to be equal to 2n plus 1 minus x Ln of x, and then minus e to the x over n minus 1 factorial, dn minus 1 e to the negative x, x to the n, like so. And then I'm going to write the Rodriguez formula for this. So we have a negative n, and then e to the x over n factorial dn x to the n e to the negative x by the Rodriguez formula. And so let's do one more line over here. So this becomes what? This becomes 2n plus 1 minus x the nth Legendre polynomial, or Laguerre polynomial, not Legendre, and then minus e to the x over n minus 1 factorial dn minus 1 e to the negative x, x to the n. And now I'm going to expand this out. So these terms over here are going to turn into what? So these terms right over here are really e to the x over n minus 1 factorial, right? Because the n and the n factorial cancel out. So then we have minus e to the x over n minus 1 factorial, and then do one derivative of this thing over here, right? So if I did one derivative of dn minus 1, one derivative of nx to the n minus 1, right? And then I'll e to the negative x, and I'll have negative e to the negative x, x to the n, like so. Okay? Now let's look at these terms over here. This term over here and this term over here are exactly the same, but opposite, right? Because I have a negative, that will turn into a positive. I have a negative over here. I have an e to the x over n minus 1 factorial on both of them. And then I have n minus 1 derivatives of what? Of e to the x, x to the n. So this term over here and this term over here are going to cancel out. And this becomes just what? This just becomes 2n plus 1 minus x ln. And then what's left over? I have this n over here, which I'm going to pull out of everything. And then I have e to the x over n minus 1 factorial dn minus 1 of x to the n e to the negative x. That's just the n minus first Legendre polynomial. So this is going to be minus n times the n minus first Legendre polynomial, like that. Great. And so putting this all together, we have a recursion formula for Legendre polynomials. What is that formula? That tells us that n plus 1, ln plus 1 of x, is equal to what? Is equal to 2n plus 1 minus x, ln of x, minus n, ln minus 1 of x. And this is our recursion relationship. This is our three-term recursion relationship for the Laguerre polynomials. So these Laguerre polynomials pop up in a lot of applications, in particular to the Schrödinger equation for the hydrogen atom. And so recursion relations like this are able to allow us to find a generating function for the Laguerre polynomials, which we'll see in the further video. And that generating function is going to be the key to understanding properties of the Schrödinger equation for the hydrogen atom, just with some sort of radial symmetry on the wave function. Thank you very much.